Sorry, guys. I know this lecture has gotten a little long. Let's try to wrap it up and finish up a few of the last examples, kind of briefly, as time is taking too long. But the last example on our packet says find the area above the curve of y equal ln x. And what I'll do is I'll actually leave this as a problem for you guys to solve on your own. But again, if you're trying to solve an area problem, again, we could start with the graph of the natural log, y equal ln x. And it says above the curve. So notice that actually if we were to do this, this area this is an improper integral because, again, the natural log function has a vertical asymptote. It trends down towards minus infinity. So if we were to integrate from 0, also the x-intercept of logarithm occurs at 1. So basically we'd be trying to solve the integral of ln of x from 0 to 1. And again, this is an improper type 2 integral because of the discontinuity at 0. But I'll go ahead and let you figure out for yourself if you think this is a convergent or a divergent area. Another interesting answer. But lastly, let's actually talk about the comparison theorem because it's another way of determining whether an improper integral converges or diverges. And it's an idea that actually we're going to return back to in chapter 11 when we get into sequences and series, because sometimes it's easy to see if something converges or diverges based on comparing it to something simpler, which is the general idea. So it says, suppose that f and g are continuous such that f is larger than g for all x and g is positive. So both functions need to be positive always on the values. And f needs to be strictly larger than g. So drawing a picture of me kind of imagining what this is saying is, well, we got two functions. I got f, which is strictly positive in black, and then let's just say g is in red, and it's always going to be below it, whatever. It could be equal, but it's a smaller function on all accounts. What it says is that if the integral of f from a to infinity of the function is convergent, then the area, the integral from a to infinity of g of x is also convergent. So this is kind of an easy thing to visualize in my opinion, because if I'm integrating from a to infinity, that means literally from there, all the way out. And so what's saying is if f's area to infinity is convergent, then since g is small, that again, if it's convergent, that implies it's finite, say 10 or 20 or whatever, a finite amount. Again, technically they would both need to go to 0 in order to converge to infinity. But I didn't draw, ignoring the end behavior. But if this is a finite amount of area, then the area underneath g, being strictly smaller, has to be smaller. So if f is a finite number, g has to be a smaller finite number, and it must also converge. Now, the opposite kind of idea is also true, which is what the part B of the comparison theorem is sort of saying. It says if the area underneath g of x to infinity is divergent, aka infinite or something other awkward. So imagining underneath the red function, say this amounted to be an infinite amount of area going all the way to infinity. Then the area of f of x, a larger function, must also diverge. So it's kind of like saying, if this adds up to something infinite, anything larger must also be infinite. If this is infinity, all of that, the area underneath f, being a larger function, has to clearly be more. And that, again, that's the issue with divergence and infinity, is you can have more than infinity. Infinity is not, there's something more than infinity. It's not a finite amount. The pattern of infinity has a lot of interesting traits and characteristics, something that can definitely mess with your mind if you overthink it. But anyways, let's actually use the comparison theorem because it can be helpful for basically comparing something complicated to something simpler. So our example says, use the comparison theorem to show the integral from 1 to infinity of 1 plus e to the minus x over x is divergent. And in order to do this, if we're trying to use the divergence clause of it, basically we're trying to do this. If I want to show this is divergent, I need to find a function which is smaller who is also divergent. So I'm kind of paying attention to clause number B. So if I can find a smaller function that diverges, I can show that this, and actually my first thought would be to go, what about 1 over x? Because this is a function we already know diverges as it approaches infinity. Sometimes this is called the harmonic function or the reciprocal function. The harmonic series, actually something we're going to come back to in chapter 11, very, very interesting case, actually has an exact conclusion for essentially the same reason. Pretty cool to come later. But basically this integral is infinite. We've already done this. But notice about the numerator is this is 1 plus e to the minus x. And an exponential function, such as e to the x, has to be purely positive. So notice that this right here is larger. So I could also express this as an inequality. Let me just go ahead and write that out. 1 plus e to the minus x is always greater than 1 for all values of x, in the reals. But another way of saying this is 1 is less than 1 plus e to the minus x. And notice this is exactly why this makes sense, because this function is strictly, if I was to write this, is strictly smaller than 1 plus e to the minus x over x. And so for the comparison theorem, this is like my g function, this is like my f function. G is strictly smaller than f. And what the comparison theorem states is that if g is divergent, aka if a smaller function diverges, the larger function must also converge. So essentially once I've shown this is true, basically the logic here is that the area underneath this curve is infinite. Since this is larger, this must also be infinite. And so let me just erase this so I have a little bit more room to write. Logically speaking, this means that the integral of 1 plus e to the minus x over x with respect to x from 1 to infinity also diverges by comparison. And I don't want to overly get into the proof and the math behind the comparison theorem. I don't actually even remember if our book even does it, but the logic of it to me is sort of like common sense, right? If this is infinite, this must be larger. It must also diverge because it's larger. And the reverse is true. You do need to be careful about the logic of the inequalities, because if you do not explain this or show this, basically I need to show that the original supposition about f and g is true in order to use the theorem to actually do something. And as usual, some practice questions for y'all. Try it out yourself. See if you can get a handle on improper integrals, whether they're type 1 or type 2 or both, and practice extracting the limit, doing the math. Anyways, see you all on Friday for review day. Email me with any questions, and have a nice day.